Okay, so just checking it's recording. It is. This video is going to be about, well, it's not really going to be about anything because it's going to be me coding in Lean. So on the Lean Sulip channel, Alex here commented that it would be good if people, posted their Lean sessions on the internet to give people a reference, to see how other people code Lean. And I thought I may as well do this. Not because I am good at Lean, but because perhaps I am a physicist working with Lean, and it may be interesting for some people if they're interested in physics to see what it's like to code physics in Lean. So this is not scripted. This is me gonna try and do something, try and prove a theorem in Lean and record, the process of how I would do that. So the theorem I'm gonna focus on in this video is really going to be about proving a simplification of the Lorentz algebra. So this is part of this project. This is part of this project Heplean, which I've been working on for a while now to build or to digitalize high energy physics. And of course, one of the things that's important in high energy physics is the Lorentz group, Lorentz symmetries. So we need a notion of the Lorentz algebra. Luckily for us, MATLAB has basically defined the Lorentz algebra for us. So they're in MATLAB. MATLAB is this big library of digitalized results in mathematics. There is a definition of Lie algebra, or rather an indefinite orthogonal Lie algebra. And this is this definition here. And I can hover over it in Visual Studios and it will tell me, what this definition is. So this is the definition in Heplean of a Lorentz algebra, of the Lorentz algebra. But this isn't that easy to use, so we want to define it in a we want to change its definition, or we want to add some lemmas that make it easier to use. So one of the lemmas that I want to, or the lemma that, or the theorem that I want to show is that if a matrix, so let me start with my lemma, and actually let me open a namespace here. I know I've done some other stuff below that's not really going to be relevant, but let me open a namespace, Lorentz algebra. By the way, I have GitHub Copilot installed, and GitHub Copilot is clever enough to know that I want to type Lorentz algebra there. So all I have to do is press tab. Yeah, so this lemma is really going to be a membership lemma. So I'm going to call it member if and only if. And the argument of this lemma is going to be a matrix. Hey, and as you can see, GitHub Copilot kind of already knows what I want to do here. So I want to accept this. And I basically want to accept to there. So I want to say that A is in the Lorentz group if and only if eta times by A is equal, or eta times by A transpose is equal to minus A times by eta. And then later on we can add some refinements of this lemma. Notice I'm adding, by the way, 4 spaces here to indicate that this is still part of the lemma definition. And for my proof, I'm gonna indent it by 2 indentations. So we want to prove this lemma. The first thing we probably want to do is we want to expand this definition of the Lorentz algebra. So let's see. Well, okay. Yeah, so let's see what that takes us. I will move myself from here so we can see the tangent state. Okay, so simplifying the Lorentz algebra changes the statement that A is in the Lorentz algebra to this thing here. I'm gonna assume that you can digest what that says in your own time. I should say, by the way, one thing about the Lorentz algebra, which makes this kind of complicated, and this is something that happens quite a lot in Lean, is that this Lie algebra, as we can see by the definition here, is defined with a matrix indexed by a direct product. So what was here, I've indexed my matrix by just fin4. That basically, this is basically 4x4 real matrices. So we need to change this definition here. So if we hover over this is a Lie algebra, a Lie subalgebra of the matrix Lie algebra of fin1 plus fin3. And we want to change that to fin4. And this is basically what this map here does. It changes that to fin4. So this is basically what you're seeing here. So this y is in the Lorentz, it's in this Lie algebra, the Lorentz algebra, but this Lie algebra. So y is a matrix indexed by fin1 plus fin3. And this is saying that y is in this algebra, and when you re-index it, y is equal to a. Okay, so good. Let us split our if and only if statement into an if statement and an only if statement. So if and only if intro. So now we have one way, the if statement, and then the only if statement is this one down here. So let's do intro H, and that will turn our implication into an assumption and a goal that we have to prove. And notice we have an exists here. So to get rid of an exists, we can do obtain. And we can go obtain y. Well, let's call it b. Lean wanted to call it y, but we can change that notation if we want. Okay, so if we do that, we notice that here, this lemma with exists y becomes a statement of a b, which is, as I said, a matrix index by fin1 plus fin3, and a hypothesis that B must satisfy. Actually, let's split this hypothesis into two, a priori, or like not a priori, but already, because it had an and statement, and so we can split it into two lemmas. Okay, this is good. This looks good already. So perhaps what we should do is, well, let's see what happens if we simplify at HB1. That didn't do anything. So let's simplify this. Okay, so what did that tell us? That tells us, so that turned out HB1 into the statement that B is a skew adjoint. So let's simplify skew adjoint, see where that takes us. Okay, that took us to B being an adjoint pair. So let's simplify that. Okay, so this is telling us that B transpose times by some matrix is equal to minus some matrix times by B. And what this matrix here is basically this indefinite diagonal matrix. If we look at the definition of eta, so let me go over to the definition of this. This is the same matrix. That vanishes, but this is the same matrix as it appears here. And eta is just defined as a re-indexing of that matrix. So this matrix here is basically eta, but re-indexed. Okay, so I've noticed something here that my goal is slightly different from what this looks like. So here I've got B transpose and then times by what is naively eta, and here I've got eta times by A transpose. So I'm gonna cheat, or not cheat, but I'm gonna change my goalpost quite literally and swap my etas around over here. And then we can prove the lemma that we were going to prove some other time. That would be a simple corollary, wherever that word is, of this lemma. Okay, so where do we stand? Well, what we want to do now is we want to turn these two equations into one another. Or we want to turn this equation here into this equation here. Sorry, this equation here into this statement here. And they're basically the same statement. They're just re-indexed. So one is a re-indexing of the other. So we have to re-index this statement or that statement, either way. So let's do that. So let's go apply. And what do we want to do? We want to go equif equals if and only if equals. Okay, apply equals if and only if equals. I think that's the lemma that we want. Yes, it is. And we want to, what do we need to give it? So we need to give it an equivalence f, and we can do that using this equivalence here. Does it like that? It does not, because I haven't. I need to do MP at the end, and that's probably telling me that my equivalence is the wrong way around, which it is. So, okay, what's it complaining about? Test type. Okay. So the problem here is that my pre-indexed equif is not quite an equivalence. So we need to try and turn that into an equivalence. So let's see if two equif works. That's not. Let's see if two linear equif works. And then two equif. Does that work? That did work, I believe. But what is that saying? Maybe I need to do sim. Good. Okay. So, yes. So now we have re-indexed our equation like this. And we can try and see if the equivalent will let us move stuff around. Okay, this will not. Okay, so at this point, we need to backtrack and, okay, this equivalence, well, actually, let's just check if this equivalence has any lemma related to multiplication. So we're going to do that by coming over to the internet, and we're going to go to Google, which is like Google, but for lean. And let's search for matrix re-index equivalent and more, and there are no lemmas. Okay, so let's try without the matrix. Let's try that. Okay, so let's see. This lemma looks like it might work. So this re-index algebra equivalence, which is different from a Lie equivalence of algebras, but as functions, they are the same. So hopefully we can replace our Lie equivalence here with algebra equivalence. And what does this need to take? It probably needs to take two. Okay, well, what is this saying? This is saying it wants to type because it's an algebra, it probably wants R. Good. Good. And then we can do R index algebra equivalent. Wow, okay. Mult. Matrix. So that didn't find that. Okay, because we're going the wrong way, so we need to do like that. And that still didn't work. So let's try ER. That doesn't work either. Let's try simp. Okay. So, oh, actually, no, we do want to go this way. So let's see if that worked. Okay, so this is being annoying. Maybe because I've got simp there, if I change it to put in simp there, will that let us do it? That will. Perfect. Okay, so that was just an annoyance with sim being the wrong side of the rewrite index rule. And as you can see, what this has done now is it's taken this re-indexing and has moved it through the multiplication. Okay, so let's see if we do simp, what happens. Okay, so I don't want to simp all the way because it's replacing this re-index with multiplication, which is not something I want to do. So let me see what lemma is actually applying. So that lemma looks pretty good to me. And it's a submatrix I want to get rid of. No, that is, we probably could work with it, but it is a bit annoying. And there's something else which is moving my matrix to a submatrix. Let's see what this does. Nope. Index apply. It is probably this one. Okay, so let's remove that from our simp database. And good. Okay, this is done. This is done at everything we want. Actually, maybe I can get rid of that. Can I? No, I can't. Okay, let's keep it in place. Okay, so if we look at the lemma, let me move myself over there. I probably should have done that at the start. But now we have something that looks quite close to our hypothesis. The only thing it looks like we have left to do, so if you notice that this reindex B is equal to A, what we want to do is we want to actually turn this, we want to move this transpose to the other side of this reindex. So we want to take this index through the transpose. And let me come over to Lugal again. Let's see if we get any, if we have any lemmas related to indexing and transposes. We do. That's good. So we can come back over here and we can go rewrite and see if that works. It doesn't because it's the wrong way around. And then we go. Okay, so now we have something that looks very similar to our hypothesis B, and let's just try. Probably won't work. Okay, we can try exact question mark to see if lean can work out a lemma that will move the goal. It can't. So, okay, so what should we do? Well, what we should probably do is change this. Oh, the lights in my room went out. We probably want to change this re-indexing to B. So let's start like a small hypothesis or a small lemma. And the lemma that I want to prove is basically the inverse of B2. So it is that this thing here, so let me copy and paste, is equal to B. And let's just put sorry there for now. And we'll come back to that in a second to prove it. I just want to make sure it works. Good. Okay, so that seems to have worked. Can I apply that twice? I cannot. So good. No, it's already applied it twice. And if I do that, can I go exact HB1? I cannot. This is probably because it doesn't know that this re-indexing is this identity rule. So we can go and prove that. We'll go prove that in a second. The proof is going to be basically the same as this. Let's see if Liam will prove this for us. It will. That's really good. It's basically this lemma is basically saying if fx equals y, then x equals f dot sim y. So we didn't have to think about that. We can get rid of the by and the exact if we wanted to. And we could even actually put that directly there. I'm not going to because it's quite long. So we now want to prove that this thing here is what we see up here. So let me not prove that in this document, but let me prove that because this is the lemma about the metric. Let me prove this in this metric folder. And this is the statement, basically, that Ada reindex. So what is to prove? The statement that we want to prove is that this is true. Let's take this all onto a new line. That still doesn't fit. Let's go back. And the proof should be very simple, actually. It's simply that. Okay, so we don't have to think about that. Lean does it for us. Let's save this folder. Let's come over to this. Let's restart this file. And then we should have access to this lemma, which we can type into there. I'll give Lean a second to catch up. That didn't work off the shelf. Let's see why. Reindex sim. So it is slightly different, the lemma that we want to prove and the lemma that we have. Sorry, the lemma that I proved and the lemma that we have. So let me do another lemma, which is called reindex prime, which is going to be the statement that when you have sim here, this might be slightly trickier to prove. Actually, it's not, which means that I could probably have got away with right here. Index. Let's see if I spell that right. I did not. Good. Okay, I could have. So I don't need this. I don't need this additional lemma. It was a simple definitional statement. Okay, and then I should be able to go exact HP1. Perfect. So that's proven our if statement. We now need to go back and prove our only if statement. And let me make the syntax a bit nicer. Syntax a bit nicer by putting a dot and moving all of this over there so we can clearly distinguish between our two lemmas. Lean Copilot wanted to try and finish the proof then. I don't know if that would have worked, but we'll see. Okay, so now we basically want to prove the inverse statement. So let's go intro H. And we now have to prove an existence lemma. So we have to prove there exists a y such that it's in the Lie algebra and that its reindex is A. So the easy thing to do there is to use basically the inverse of the reindex, which is, let's go to what the reindex statement says. This is it up here. Does that work? Yes, that allows us to do that. And what we need to prove is that A is in this reindex of A is in the orthogonal group, and that this statement here is true. So let me go apply and if and only if, sorry, and intro. And let me go swap because I think the second statement is going to be pretty easy to prove with exact. Does that work? Something's not working with my file. Okay. Something timed out. So if this happens again, I'll just restart my server and hopefully we'll get back on track. Yeah, so what's happening here is this exact statement that's running out of heartbeats. And sometimes this is, I think recently this has been due to a bug. So let me restart the server. And it hopefully should give me a proper statement. If it doesn't, it's fine. We'll have to work out a different way to approach this. Okay, let's see if rewrite question mark will do anything for us. It is not, this has been a bit slow. So in the meantime, let's go back to Google. Oh, that did do something. Okay, let's see. Okay, basically, I want a lemma which is about equivalences and the sim of an equivalence. So let's go to Google and let's see if they have anything like that. Maybe if I put apply, that will give us something better. Well, what we can do is we could probably use this lemma actually. We could do a rewrite. That does that not work? Why does that not work? Um, let me put simp. Maybe it's because my equivalence is wrong. Let's see if I simplify using this. It won't do anything. Okay, so that didn't do anything there. What do I want to do? I want to go see. Let's see if I. Let's see if it's a lemma like this. There is, and that should have hopefully given me. Okay. Worst case scenario. Let's see if it will let us just use definitions to change this. So let's see if we go change reindex. It does not like that. Okay. Let's go simp. And let's just simply with. Okay. So this is being a bit of a nuisance now. Basically because what's happened is, okay, let's get rid of the simp. It has turned my reindex equif and it's applied to lehom on it. So let's see where it's done that. Actually this is probably in my definition up here. Yeah. Okay. So good. So the problem is that this lehom, I don't think it knows this is an equivalence anymore. And oh, let me come back over here. So let me try and do the following. Let me just copy this. Let me go change. Good. Okay, that worked. So hopefully that now knows that's an equivalence, and then I can go rewrite. Let me come use this lemma again, this one here. Let's see if this now works. Okay, that didn't work. Let's see if I put that there. That doesn't work. That work? That did work. Cool. That finished our lemma for us. That proved our goal. So let me just ensure it knows what it's doing. Yes. Okay. And well, actually, there's something I haven't tried yet. So actually, I don't have this installed. I was going to use Lean Copilot, but I don't think I have it installed. Well, let's give it a go. And if I have it installed, we can use it. Nope. Okay, that's a shame. Okay. I won't go through the installation of that because it'll take too long. So now what we want to do is we want to show that this matrix here is in this Lie algebra. So we kind of did something very similar to this above. This is essentially the same proof, it feels like, to what we had above. So we can probably get away with, copying what we had above. So, well, actually, is it exactly the same as we had above? I believe it is. So, how should we prove this? What is the best way to prove this? Well, let's just try and repeat what we did above, and then we can make it simpler later if we want to. So this simp is doing too much. So I want to get rid of this reindex apply thing, just because I prefer working with the reindex matrices. Good. Okay, so let's see, what do we have? Let me simplify. Okay, and what we want to do is we want to apply to let's apply this lemma at H. Will that let me do it? No, that won't. So let me start a new hypothesis. And my new hypothesis is going to be this. So H1 basically is the goal that we had last time. So we now want to move H1 to look like our goal now. So this is going to be hopefully a simple case of rewriting what we had above. So let's see if it will do this multiplication rule. Did that work? And we want to do it at H1. That did work. Good. Let's simp at H1. What does that look like? That looks good. And then let's rewrite this at H1. And then exact H1. I think we might, that did work. Good. Okay, so that is our lemma proved. It's kind of long. I kind of did the same thing twice, but there is a proof of a lemma. I mean, well, actually, probably it is easier to do. Um, what it's easier to do is split this into two lemmas, one for the only if and one for the if statement. So let me do that. So let's go lemma. Um, let's do transpose eta. And our lemma is going to be that if A is in the Lorentz algebra, then this is true. So this is the only if statement. So we can sim at a dot one. Well, okay, let's go half h is equal to a dot two. Good, and hopefully that is exactly the same as we had above. And then we should be able to copy and paste this to there. And if it works, it works. And if it doesn't work, it doesn't work. Why do you not like that? Obtain. Aha, you're complaining about this. Okay, so. And then what is wrong with this statement? The HB1 P transpose. Let me try simper. Or simply using rather. Good. Okay. So that just didn't like the exact. Let me see if it will fix it. Okay, simper's fine. So we can now replace this lemma with exact, well, exact eta transpose eta. For H. Okay, so what I want to do is I want to make okay, so this is not quite working as easy as I thought it would. So let's do some figuring out why these look different. Oh, okay, let me just put let there. That's probably why. There we go. Yeah, okay. I had half instead of let. They are different, and that's why it didn't work. Actually, maybe I just put that there. I can. Ooh, I don't want the dictionary to open. Perfect. Okay, and then we can go lemma member of transpose eta equals eta. And this is going to be the statement that if A is a 4x4 matrix, so this is the only if statement. and that HA satisfies this equation, then A is in the Lorentz algebra, and this is this inverse statement here. So let me call this H. We can, well, okay, let's simplify with respect to the Lorentz algebra, and then go use, and let's see how much of this carries over. Perfect, almost all of it, except for that. And then this if and only if statement just becomes intro H exact question mark, and no italics, it's just that lemma. Good. Okay, so that is the two that is the lemma that we wanted to prove. We actually wanted to prove a slightly different version when Ada was the other side, but they are essentially the same. One can probably prove quickly that they are equivalent. And this is kind of like how I write lean. So now that this is done, I have this proof here with a sorry at the bottom. Let me just remove that for now. We can upload this to GitHub. We can make a pull request to GitHub. And this is because this file is new, so it's green, and then I've made some changes to the metric, and we can go, okay, feature, lemma. So this has been uploaded to a branch of Heplean. Ada, well, okay. Let's call it feature add Lorentz algebra commit. And then we can come over here and let's go back to Heplean. And we should see that it's now going through a number of checks. It's actually failed one of the checks, which is continuous integration. And it's saying, okay, I have some simps in there that aren't terminal, and I haven't replaced them with link question mark. Sorry, with a fixed database of lemmas they can use. It's fairly easy to fix, so not too worried about that. But yeah, I'm going to stop this video now. That was me working on Lean. If you want to add to the Heplean repository, feel free to. Hopefully this has showed you about Lean and high-energy physics and Lean, how one can go about Lean. And yeah, sorry it was so unprepared and unscripted, but I think hopefully that was beneficial in a way to show you the process that at least I go through when I'm coding Lean. So with that, thank you for watching. I'm gonna try an attempt to stop my Lean video, my recording.